Hi everybody, it's Dr. Chabot, and in this last video for our module on introducing the electric field, we're going to calculate the electric field for a plane, a two-dimensional plane of charge. So we're going to move away from our single dimension and move on up to a plane. And then we'll summarize all the different geometries that we've seen. So to do this, we're going to recall the charged ring. So we had calculated the electric field from a charged ring that has a total charge Q distributed around it above the center of that single ring. And so we're going to use this as a starting point to talk about the plane. And the reason is that if we look at a charged plane, then the charged plane, and we're gonna picture a circular plane to start. The circular plane, if we're looking then, say, some distance z above the circular plane, can be thought of as an infinite number of concentric rings, right? So it can be thought of as an infinite collection of rings, right? And so these rings would all have some variable r, and then we could add up the electric field contribution from each ring. So we want to add up the electric field contributions from each ring. And then that's going to give us our entire plane. So the result that we had derived prior for the total electric field from some total charged ring of charge Q, we have to modify it slightly now because we're not going to have a finite amount of charge Q on this one infinitesimally small ring. Instead, we're going to be starting to talk about some surface charge density here. So let's kind of adjust that ring so that it works for us. Let's give this plane has some surface charge that we're trying to find the electric field above. Let's say it has some surface charge density that's going to be given by sigma. Now remember, charge density when we move up one dimension, that's going to be because now it's a charge per area that we're using sigma and not lambda. And so that's going to be our plane surface geometry. The total radius is going to have a radius r, so an outer radius r on this charged plane. And so we're going to use little r for the ring. So each ring has a radius little r, and we'll want to sum from 0 to big R. So we'd want to add up all of our rings in that bit. Each ring contributes a tiny electric field, dE, right? That's going to be equal to, using our previous result, that dE, and again, we're only concerned about the direction, right? So that dE is going to end up being in the z direction, and it's going to be small. And so instead of a total charge Q, we're going to put a dQ. Oops. For this total charge Q, we're going to make it small. And so that's going to end up being K dQ times Z over Z squared plus R squared, all to the 3/2. And so that's now our tiny contribution from each ring. That is in our z hat direction. We've already done the symmetry when we did that ring problem. And now we want to add all of these up. So fundamentally speaking now, the main thing we're going to change is that this is now going to have the variable radius r. So we're going to change that, and we're going to put this as our r squared, little r squared, and that's going to give us something that we can integrate. And then z is going to still be in our answer because z is how far away we are from the plane, and we want to have a z in our answer. So to get the total electric field, which is still going to be along z, then we're just going to add up all of our electric fields from these individual rings. And so that's what we're going to put in here. So we have the integral of k dq. We'll talk about dq in a second. I'm going to just plug this in here. dq z over z squared plus r squared, little r squared. And we're going to integrate this eventually from little r to big R, but we want, from little r being 0 to little r being big R, but we want to first have something where we have a dr, so we need to work with this dq. So the dq here, the dq, because we're using a sigma, will be equal to dA. So that's our if we write that out in our words, which you know I like to do, the sigma is our charge density, so it's our charge per area, and then times the tiny area. So we need to think about what is the tiny area of the ring. So what is our tiny area of each ring? And so if we picture the ring and we're like, okay, but it's just it was a one-dimensional ring. It wasn't really, now that we're trying to extend it into 2D space. It's infinitesimally thin, so it has some radius r, but it's going to have some thickness to it as well, right? Because we're going to be adding these up to make our plane, and that thickness is dr. So if we now imagine unfolding this, so if we unfold this, then we just end up with a straight line. If I unravel the loop, and the thickness of it is dr, and the full length of it is going to be 2 pi r. And so this then ends up having an area. So the area of this, the tiny area, is 2 pi r dr. And so that's going to be a key result that we'll see come out throughout the semester of how we can kind of add up into two-dimensional space these individual rings that allow us to do that. So now we can actually say, okay, what's our dq? So our total dq then is just going to be sigma dA. So plugging that in, we now have k, and then dq is sigma, and then dA is 2 pi r dr, and now we have our dr. And then times z, so I just plugged in for dq here, over z squared plus r squared. And this is again all in my z hat direction. I now have, because all of this was my dq, which was sigma dA, which was sigma times 2 pi r dr. I now have a dr, and so my limits are going to be, for r, are going to go from 0 to capital R, because I want to add up all my rings in the plane in order to get this. And so I lost my 3 halves, so I'm going to bring that back. I apologize. Up here and also here, I have my 3 halves in this equation, just from copying it from the result for our rings. And so now I have this integral that I can do. I'm not going to show all the steps, but I can do it via u substitution. So I would do it through u substitution, where I would say, if you're curious about the calculus behind it, I would use u substitution. I would say that u was equal to z squared plus r squared, and then I can execute this integral. But if I just go ahead and write down what we would get if we execute this integral and do a little bit of algebraic rearranging, then I get that e sub z, and again, this is all just in the z-axis above the plane, is going to be equal to 2 pi k sigma. So these are just constants that we had all along. And then times 1 minus 1 over the square root of 1 plus r squared, the radius of the plane, so capital R squared, over z squared. And that whole thing is in the z hat direction. So that result is the exact result for any plane above it. And what we're going to look at in a second is what happens if that plane gets very large compared to the distance that we are from it. But fundamentally, all we did for this problem before we move on to that summary was to take the charged rings result and then make it into a continuous plane. And by doing so, we now have an electric field that's in terms of its charge per area. So that's a coulombs per meter squared term for this charged plane. Okay, so we can look to see what our results are. So I have here a summary of our geometries, and we've had 4 geometries that we've encountered in this module. And I'm just going to start with the 2 simplest to start. The first was the dipole, is not the simplest of the results, but in terms of the relative discreteness of it, right, the calculation was pretty straightforward. And what we saw was that the electric field went as 1 over r cubed when we were some distance away from it, and we were either looked along the axis perpendicular to the dipole, and we also calculated it along the length. In both cases, we found that 1 over r cubed dependence. We, of course, know for a point charge that a point charge is going to vary just simply as 1 over r squared. And that's going to be any distance r away from a single point charge will vary as that 1 over r squared. And so then what we did is we looked at and we've calculated the electric field from an infinite line of charge. So we actually haven't looked at it for infinity yet. We've really only looked at it for a single line of charge. But what happens now if the lengths go to infinity? So if the lengths go to infinity, we can take this result for a finite line, and then we can say take the limit as L goes to infinity of this electric field. So if we looked at this, one easy way to kind of think about taking that limit is to say that we can rewrite this for E for the line is going to be equal to, and I'll write this as K lambda L, and then out of this bottom part, I'm going to pull out an L over 2. So I have R, which is now just what I'm calling the distance away from the line, and then I'm going to pull out an L over 2 over here. And so then that's going to allow me to then in this square root term, which this should be square rooted, so this is a square root term, will be 1 plus, and then it's going to be over here, the r squared, it'll be r squared over quantity L over 2 quantity squared. And then that whole thing to the 1/2 power. And so if this is our result for the, for the line, then we can see that on the left side, when L is just there, it cancels itself. And so now we have something that's an easier limit to take. So the limit of this as L goes to infinity is going to be that this is going to be 1. So the limit of that last term goes to 0, and then that just becomes 1. So the E field of an infinite line, so E for an infinite line, will then give me this result of K lambda, I have a 2 on the top because of that L over 2 I pulled out, all over R. And so very interestingly, this is going to go for a line goes as 1 over r. So that's going to be our result for a line of charge, an infinite line of charge. And then lastly, we just did a plane of charge, but now let's see what happens if it gets a large distance away. So here I'm again just using r as the distance above the plane. So I've rewritten the result we just derived. Instead of z, I'm now putting in this little r just to keep it consistent for all these geometries. And we can easily see, because I've already written it in a way where that makes it easy to see, that as the radius goes to infinity, that this is just going to go to the E for an infinite plane will then just be equal to 2 pi k sigma, which is very interesting because there's no r dependence. So that means here, right, that the electric field goes as constant, it's uniform for an infinite plane. So if I zoom out and we look at all of these results together, we can now see that changing the geometry changes how the electric field drops off. For an infinite plane, it actually just doesn't drop off. The electric field is constant and it never gets smaller as you move further away from your infinite plane. For an infinite line of charge, it drops off as 1 over r. For point charge, it drops off as 1 over r squared. And for a dipole, it drops off as 1 over r cubed. All right, so I hope that this last video in this module works as a nice summary of all of our results, as well as seeing what it looks like when we move our calculations into the higher dimensions away from just 1D.